Welcome to this video. I am Alex Lipka, a professor, an assistant professor at University of Illinois, and today I'm going to go over an overview of what linear algebra is, why it's important from a statistical perspective, and from a quantitative genetics perspective, and then an overview of the software we will be using that does linear algebra for us. So, we should care about linear algebra because it is a simple, parsimonious way to represent large amounts of data. And in this world where we are obtaining bigger and bigger data from the latest genotyping and phenotyping platforms, this is going to be essential. So, in addition, it allows us to generalize simple statistical analyses in terms of big data. So basically we can take simple equations and generalize them so that we can consider millions of data points in one symbol. Also, the underlying theory of linear algebra basically forms the basis of statistical operations. So statistical approaches are based off of, linear algebra, addition, multiplication, etc., etc. Now, from the perspective of quantitative genetics, the reason why we should care about linear algebra is that the underlying theory of linear algebra forms the basis of approaches for genome-wide association studies and GS, genomic selection, both of which we'll talk about in the next series of slides. Quantitative genetics is a vast field that goes over a whole lot of different dense and far-reaching concepts. Linear algebra helps us condense all of these, far-reaching concepts into simple to understand equations. And another important thing is that most linear algebra operations, most of the grunt work for doing linear algebra, have already been written in software. So this means you don't have to spend time doing complicated number crunching on a sheet of paper. We let software do it for us. So with that in mind, here is an introduction to RStudio, the software we will be using for linear algebra is the R software package, and here's a picture of the graphic user interface, if you will, RStudio. So basically, you can write a whole bunch of R code here, and then you can run them in this module over here. And here are two other windows that I really don't use, but other people find extremely useful. So, genome-wide association studies, what we'll be going over in the next series of videos is that genome-wide association studies are a bunch of statistical analyses that help us find genomic regions associated with a trait. If we want to use GWAS in a software that uses linear algebra, we would use the GAPIT R package. So here's some code that uses the GAPIT R package in RStudio, and so this is how the code looks like, and basically you just highlight the particular lines you want to run and you press the wrong button and out pops your analysis looking something like this. So there's a whole bunch of different pictures here, but here's one thing I'm going to highlight in the next video series, which is a Manhattan plot. Your x-axis is your base pair position along the genome. Here this is maize, so we got chromosomes 1 to 10. And then your y-axis is your strength of statistical association between your phenotype and your tested marker at the given x coordinate. So if we wanted to use genomic selection software, where GS is equal to genomic selection, one widely used software is rrBLUP. So briefly, what we're doing with genomic selection is we are using a genome-wide set of markers to predict breeding values for breeding material that plant breeders or other breeders want to carry forth to the next generation of selection. I'll go more to that later, but the software package that uses linear algebra operations for genomic selection is rrBLUP. And Very similar to GAPIT, if we look at the rrBLUP code that runs everything, we can have something that looks like this. And then it'll produce some output summaries, such as presenting your prediction accuracies, which I'll go over again in the next slide, in the next video. And then also we can look at our bias of our predictions. Thank you.